Okay. So hopefully it works this time. Otherwise, I'll just call someone from ITS. So, all right. So last lecture, we talked about the properties of water, both biochemical and physical properties, and basically how it works as a media, and some kind of important like properties that is conferred by the water molecules property itself, like a hydrogen bonding, H bond, or the what is it, the hydrophobic effect, hydrophobic aggregation, basically, as well as some other interactions, and the properties of solutions too, colligative properties, and the some definitions about solvents and solutes and things like that. So today we're going to keep talking about water molecules, but this time we're going to more focus on the how it is involved in the actual biochemical reactions. So rather than serve as a media, this time we're going to focus on these molecules' role in as a reactant or the products. So let's start with the properties of water again. The water actually have a property of ionization. So that means water molecule, which is H2O basically, becomes the hydrogen cation and hydroxide anion basically. But this ionization rate is really low. So there's a slight tendency, only a slight tendency to ionize. So most of the water molecules just stay as this kind of intact whole molecule. And actually, I've talked to you a lot about this hydrogen cation, right? But there's no such thing as a hydrogen cation exists at all. But it actually exists in the form of hydronium, which is like H3O plus or H5O2 plus or even H7O4 plus and 3 plus and things like that. So, but for the simplicity, we actually use this as just H plus, hydrogen cation. I've always call it as a cation, right? Just assuming that this has a positive charge. Can it be like, can this be negatively charged too, like a hydrogen anion? Does anyone know? Have you heard of hydrogen anion, H minus? Anyone? Yes? No? Yes? How come? How come the same exact atom can be positive charged or negatively charged as an ion? Did you say something or? Number of electrons. So how many electrons do you have in hydrogen cation? 0. How many in the anion then? 2. Other person? Or? Sometimes it can work as a cation, sometimes as an anion. Is that what you're saying? So the number of electrons, are they the same, basically? That is correct, actually. So for hydrogen ion, whether it becomes a cation or anion, there's always just the one electron. And as you know, for that balance of the shell, of the orbital, there are only 2 electrons, right? That has a full balance. And ions basically have just 1 electron, so it misses 1. So it's actually H positive, right? But since it has only 1 electron, it actually interacts with the other ion that have another electron that is sort of floating on the outer shell, basically. And those are positive electrons too. But because of this property of hydrogen atom, which can have only 2 electrons to satisfy that orbital full balance, it can still interact with the positive ones. And in which case you can just call it as anion. So there's not really much a point you call it as cation or anion, but it's more like a conceptual thing. Does that make sense to everybody? maybe not. But for now, we're gonna, consider them as cations. But later on, you're gonna see that the hydrogen atoms can be actually anions too. But they're exactly the same thing, but just involved in different, reactions. That's all. All right. So there's another important property from the water molecules called the proton jump. And this is basically the proton, a proton which typically, refers the hydrogen atom in the water molecule can jump, from molecule to the other molecule. But it's not actually a physical jump. It's more like the super fast transition between just a regular water molecule to hydronium. So for example, here, there's a hydronium here, H3O plus basically. And this H proton, this hydrogen atom is not jumping to the next, one that is right next to the one molecule that is right next to the hydronium, but it's actually just this one hydronium converts back to the just a regular water molecule, but there are a lot of protons available here and there. So this one transiently makes this bond with another available hydrogen atom to become the hydronium, and that happens again and again and again to get to the one molecule that is far from the first hydronium ion here. So a proton basically it's just a charge that induces the nascent the adjacent atom to become the hydronium and things like that. So this water ionization can be described by the equilibrium constant. So we already discussed in this KEQ, equilibrium constant, which is also called as a dissociation constant at equilibrium. And can anyone define what this KEQ is? What is it? We talked about it in the last lecture. What is it? Sorry. What content? Boltzmann constant. Yeah, Boltzmann constant is involved in different place actually, where you define the work or energy there in the form of gas. Exactly, that's the ratio. I've seen other hands actually raised, but that's the ratio of the products and the reactants basically. So and this has to be the concentrations at the equilibrium, not at the initial stage of the reactions or the sort of the final stage, right, or the intermediate stages at all. And there's a term called the association constant too, as you can guess. It's the opposite term of this dissociation constant, and it's simply just the inverse of this dissociation constant. As you can see, this is the ratio of the concentration of your reactants and your products. And when you look at this KEQ for water, this water molecule, because there's only slight chance of the ionization of the water molecules, you're going to have a lot more of this water molecule concentration compared to the other ionized ions here, which are the I call it hydrogen cation, but it's actually hydronium again, or the hydroxide. So we just assume that the water molecule concentration is constant because that's much a lot compared to these ions. So we can actually incorporate this water molecule concentration into KEQ. So instead of just writing as KEQ, we put K and then move this H2O over to the other side of the equation to get K and concentration of water, and we call it as KW. Basically, it's a sort of the dissociation constant for water, but it's called ionic product because it talks about the product of the ions, water ions. And this is always, at all times, 10 to the minus 14. especially at the standard state. So I just said that the Kw, ionic product, is always 10 to the minus 14. And that is basically the product of the hydrogen cation concentration and the hydroxide concentration. And in pure water, if there's nothing involved, like ions or any other things there, then supposedly there are same amount of these two ions exist, right? So the concentration of hydrogen cation should be the same as concentration of hydroxide. And that means this and this are the same basically. So, and when you make the product of these two, that becomes 10 to the minus 14th power. So each of them has to be 10 to the minus 7. Does that make sense to everybody? But it's only when you're talking about pure water at the standard state. So since this Kw, ionic product, is constant, you can, and this is always this number, right? So you can make a relationship between these two concentrations of the ions, right? So they are reciprocally related. For example, if the concentration of hydrogen cation is 1, you put 1 here, then the concentration of hydroxide should be how much? It's not a trick question again. If it is 1, Kw is 10 to the minus 14. H plus is 1. Then how much the OH minus should be? 10 to the minus 14, right? Same thing applies. If H plus is 10 to the minus 7, then OH should be 10 to the minus 7. Simple, right? And that relationship is shown here basically. So when H plus concentration is 1, the OH should be 10 to the minus 14, and the vice versa here, basically. And in the middle, both of them are 10 to the minus 7. Make sense? And that depends on the pH. Again, pH, we're going to talk about the pH, but pH is the measurement of this H plus concentration. And we can actually make a relationship between these concentration of these water the ions and the pH. On the same slide here. So if, like I said, it's reciprocally related. So if one drops, the other goes up, and vice versa, and things like that. Always make them 10 to the minus 14. But this 10 to the minus 14 molar square is pretty complicated number, right? It's too small. It's hard to just write it too. I mean, it's easy, but hard to calculate and just to put it in every equations and things like that. So ended up we had to come up with a simpler term or the number scale for that. So Soren Sorensen basically introduced the term called pH to avoid the inconvenience of dealing with these small numbers basically. So the pH is really simple actually when you look at the definition, is the log of H plus hydrogen cation concentration with a base of 10, and you put the negative in front of that. And putting the negative makes sense because all the power here for the molar concentration is in negative. It's just too small. So instead of dealing with the pH minus 14, minus 13, and things like that, why don't we just use 1, 2, 3, 4, right? The positive integers for that. Not necessarily integers, but positive numbers. So again, here's the definition of pH, which is minus log 10 of the H plus concentration. And like I told you, in pure water at the standard state, nothing's involved there, any reactions or anything. It has to be H plus concentration as 10 to the minus 7. And the OH minus 2, right? And that's the neutral condition, basically. And pH should be 7 because you put the 10 to the minus 7th power here, then you get the 7, minus 7 comes in front of logarithm basically, and minus, is going to be canceled out to get 7. Make sense? Likewise, if anything, any numbers are large, the H plus concentration is larger than 10 to the minus 7, now you have excess of hydrogen cation basically. it's called acidic. And when you look at the pH value, it is always smaller than 7. You can imagine that, right? Because it's negative numbers, -6, -5, -3, and things like that are the bigger number than 10 to the -7th power, right? So that's why you're getting smaller numbers for pH. As opposed to this, when the concentration of hydrogen cation is smaller than 10 to the -7, then the pH goes up, larger than 7, and that means it's basic. And this logarithm, when you look at the logarithm itself, smaller changes in pH actually means that there is a large change in the actual variable inside the logarithm, right? In this case, that's a hydrogen cation. So that means just the small changes in pH means that it's a huge change in the hydrogen cation concentration. And also, when you take into account of the differences in the pH, that means a huge changes in the amount of hydrogen cations in the solution. So here's an example. The difference of 1 in pH. So think about 1, pH 1 versus 2, or 2 versus 3, and things like that. That is actually a changes of 10-fold in the concentration of hydrogen cation, because it's with the base of 10. Does that make sense? Then can anyone answer to this? Mm-hmm. Yes, so I mean, I can write it down basically if I can find the marker. But imagine this. So you have, let's say, 10 to the -7 here as a concentration of hydrogen cation. Then your pH will be 7, right? 10 to the -8. Now you're talking about 10-fold changes, right? 10 to the -7 to 10 to the -8 is 10-fold change, right? But when you look at the pH, it's from 7 to 8. So it's just a difference of 1, right? Does that make sense? So pH changes just a little bit, but when you look at the concentration, it's 10-fold. It's huge change, a lot of change. So that's why I said, when you see the 10-fold changes in H plus concentration, 10 to, let's say, just to put it the positive number, it's impossible, but let's just put it that way, 10 to the, 10 to the third power. And the other one is 10 to the fourth power. So that's 1,000 to 10,000. So that's 10 times difference, right, basically. But when you get the number, that's going to be 10 to the third power. So 3 versus 4, 10 to the fourth power. So the difference is just 1. Make sense? Then if you see the difference of 2 in pH, what would that mean? How much of difference in H plus concentration? Sorry, I can't hear you. Exactly, that's 100. Does everybody understand that? All right. So these are some examples of the pH of some relevant biological fluids, like blood is around the 7.4. It kind of makes sense, right? It's sort of neutral, but just a little bit of the basic, Gastric, juice is 1.5, and totally makes sense, right? You have heartburn or anything like reflux and things like that. You always see that something's burning there. It's acidic. And the cytoplasm is 7.2, which makes sense. So it's about kind of neutral. Lysosome. Does anyone know what lysosome is? What is it? Right, yeah. Yeah, I like that analogy, actually. I've never heard of it, though. But I like it. So it's sort of the place where you discard unnecessary proteins and other macromolecules and things like that. You're chopping things up basically. So it's a sort of an intestine or the maybe just your stomach of the cell. So that's why it has a little lower pH there. Orange juice and grapefruits are 4.3 and 3.2 respectively. So they have a 1.1 difference in pH, right? That actually means that it has 12 times difference in H+ concentration. All right, so here are some examples of the other sort of relevant biological, the pH of the relevant biological fluids or the substances. Here?
Yeah, right, yeah, that.
The last one?
No, like the pH of some biological fluids.
These guys?
Yeah, like why is it like 12?
Okay, you're talking about this point, right? This bullet point. So the orange juice is 4.3, grapefruit is 3.2. When you apply these numbers to pH, and this is logarithm, right? So you can convert it into exponential function if you want and things like that. Basically, you can calculate back how much of hydrogen cation concentration you have, right? And when you make a comparison of that, that actually is 12 times difference, 12-fold difference. You can just simply calculate it or think it that way. This is close to difference of 1, right? Difference of 1 in pH. And 1 in pH is the same as 10-fold in the H+ concentration. So 12 times is a little bit higher than that, of course, because it's 1.1. Make sense?
Yeah, so basically this calculation is supposed to be like for you to count the concentration of hydrogen in each, right?
Exactly. So I mean, it's basically a relationship between the pH and the hydrogen cation concentration, right? So you can calculate back and forth and things like that. So. Why is it 10 times difference versus 11 times? Because this is 1, difference of 1, and this is a difference of 1.1. So slightly different, right? So if you calculate back, I mean, I can't really do that right now, but if you do that, that's a little bit higher than just 10-fold change. So that's why. I just want to remind you that you won't need any calculators or anything for your exam. So don't worry about having some complicated calculations there, but you should understand the concepts here, basically. All right, so we just talked about the basic solution, acidic solutions and things like that. But why are they so important, especially in chemistry and biochemistry? Because they're used every day in every biochemical reactions. For example, the biomacromolecules like DNA, RNA, and the proteins have many dissociable groups that determines their properties. Like these are just examples. Hopefully now you can recognize and distinguish these functional groups. These are amino groups or the carboxylate, hydroxyl group, sulfhydryl group, and things like that. So this is again really important to distinguish these differences in these different functional groups, and you should be able to identify these. But all these functional groups have hydrogen ion that can be dissociated, or the hydroxide that can be dissociated, or the big chunk that can be dissociated too. And all these reactions are based on the acid-base reaction. And this, of course, when you're releasing the hydroxide or the hydrogen cation, you're actively influencing the environment for the pH too. Since this acid-base reaction is really important, we're going to talk a little bit more about this relationships and the equilibria that are involved for understanding the acid and base. So first of all, what's the definition of acid and base? There are a few definitions that are widely accepted. But first thing that we're going to discuss is Bronsted-Lowry view, where simply acid is anything. Doesn't really have to be, hydrogen chloride or something like that. That is you know that for sure that acid, but anything that is capable of donating proton. And donating proton is giving up a proton, right? Losing a proton, as opposed to base is anything is capable of accepting proton. Accepting is gaining a proton, right? And proton is a positive charge, basically. So you can think of, hydrogen cation. That's proton. That's positively charged, right? Then what about the other things? So you can think of a proton, but the opposite thing inside the atom of the proton is electron, right? So can you make a relationship with electrons for defining acid and base too? So the acid will be anything that is capable of doing something for electron. What it can be? Acid. Is it donating electrons or accepting electrons? Acid is anything that is donating proton. So it's an acid, the same acid. Is it anything that donates electrons or accepting electrons? Accepting electrons. It's the opposite, right, basically. So you can apply that. Think about the hydroxide, which is negatively charged, in which case anything that actually gives up the hydroxide would be acid. Oh no, accepting the, I'm sorry about that. Accepting the hydroxide would be acid. That make sense? Anything that is giving up a hydroxide would be base. Does that make sense to everybody? All right, so let's look at some reactions here where water molecule is involved. First one is HA, basically, one chemical or the substance here that is reacting to water molecule here to produce a minus, anion, and the hydronium, basically. And when you think about this reaction, HA gives up the hydrogen cation, right? Which is positively charged ion, so it's proton. And this one gives the proton to the other molecule, so donates the proton, so it's going to be acid. As opposed to water molecule accepts the proton hydrogen cation from HA to become hydronium, right? So this water molecule works as a base here. And anything that is left out of this initial substance that gives up the proton will be called as conjugate base, as opposed to anything gains the proton will be called as conjugate acid. And those are conjugate base and conjugate acid because in the reverse reaction, conjugate base works as a base because it will accept hydrogen cation, proton, right? As opposed to conjugate acid will work as an acid in the reverse reaction. Make sense? Okay. Let's look at the second reaction here, where again, there's a water molecule here, but instead of HA, which is an acid, ammonia, which is NH3, is reacting to water molecule. And in this case, ammonia becomes ammonium ion, which gains a proton, right? Hydrogen cation there. So it accepts the hydrogen cation proton, which means that this ammonia is base. And water molecule now gives up the hydrogen cation, right? It releases it. So that means donating. Now water molecule works as an acid. And again, the product of a base will be conjugate acid, product of acid will be conjugate base. So as you can see here, make a comparison between these two reactions. Water molecule can be either base or acid. It can be either reactants or products. And of course, it can work as a medium too. So water is just, so like versatile. It's just everywhere and working in so many different ways. And that's why we're covering, this water molecule in the two lectures. So, but putting this water molecule is kind of cumbersome because it is always involved. So instead of just writing it down every time, we're gonna just skip them because it's everywhere. So these reactions can be also abbreviated as just dropping the H2O here. And also you have to drop the H2O in the other side, right? So that's gonna be HA becomes H plus and A minus. So instead of hydronium, we just write it as hydrogen cation. And that's why we're using H plus. I mean, it's just so simple to use it, right? Same thing applies to NH3 plus H2O reaction here too, basically. And we just assume that the water molecule is always participates these reactions. Okay, let's keep talking about the equilibrium constant and understand the how acid-base reaction happens in the presence of water molecule. So here's again the reaction. It's the same as the first reaction in the previous slide. Basically, HA, the acid, interacts with water molecules to become the conjugate base. Basically. And we can write this expression in the terms of this KEQ, equilibrium constant. And the definition of KEQ, again, is the ratio of the concentration of the product and the concentration of the reactants, right? So we just write it down here. A minus and H3O plus concentration here, divided by the product, reactants, basically, here. And we just assume that the water molecule is pretty constant, concentration is pretty constant because it has a really poor ionization rate, right? So again, we just consider this H2O concentration constant, especially at the standard state, which is 55.5 molar, using chemical, chemists' standard state. We move this water molecule concentration over the other side of the equation to get KEQ times H2O concentration equals basically rest of them, right? And we just omit this H2O here too for the simplicity. So it's gonna be hydrogen cation and the conjugate base divided by the acid concentration. And we define this as Ka, which is an acid dissociation constant. And you're gonna see that in textbook, actually, it also drops just A there and use it as K. Getting rid of? Like in the equation, you're just kind of like getting rid of H2O? Yes, basically, we do that for the simplicity, because H2O is constant. So we're talking about some constants here, right? The reason that we're getting all the constants, like equilibrium constants, dissociation constants, and things like that. It's for the calculation, simple conversion from one thing to the other thing, right? So basically, it's just sets the ratio of those two different variables. So regardless, you make make the 10 times bigger or 10 times smaller or like that, the ratio doesn't change, and that's why whenever we see some constants, we try to just get rid of that. And the water molecule concentration is one of them. All right? So we just talked about the definition of acid and base and how it works, especially with the water molecule and things like that. Now look at the property of acids too. There are strong acids and weak acids, and of course, sort of mediocre acids too. Strong acids are basically the acids. The definition of acid is to donate protons, right? So the strong acids should donate a lot of protons, meaning that they're releasing a lot of hydrogen cation or some kind of protons. That means it has low affinity to proton. Make sense? So it gives a lot of protons pretty easily. So when you look at the Ka, acid dissociation constant, you're going to see that a lot of H plus generated as opposed to just the whole molecule form of the acid. So this ratio would be much, much higher than 1. And that means everything is almost completely ionized rather than being in the molecule form. And the examples include like hydrogen chloride or the nitric acid and things like that, as you can see here. As opposed to that, weak acids is basically have a high proton affinity, meaning that you try to just hold on to those all protons or hydrogen cations. So H plus basically dissociates pretty poorly for the weak acids. So Ka value will be much lower than 1. Again, you're going to have a lot of them dissociated, but will have just a little bit of proton that is released. So this number is really small, right? So it's partially ionized. But these weak acids are biologically important because they are not hurting your cells, but still can work as the some kind of mediators or the medium or the buffer and things like that, involved in a lot of biochemical reactions. And examples here, as you can see, includes the acetic acid. So again, Ka, the definition of Ka is the concentration of ionized acid, and just unionized, basically just undissociated acid there. And we actually Ka, when you look at the equation of the Ka, it actually looks quite similar to this pH, where it has the hydrogen cation concentration. So we use the same sort of conversion here, put the minus log of this Ka with a base of 10. And similarly, called pH, we call it pKa, or just a pK. And this this means that this is negative logarithm, right? So when Ka is large, then pKa is going to be small. That's the same as the concentration of the hydrogen cation and pH, right? If it is large, then pH number goes down, and that means that's acidic. What's the difference between pH and pKa then? pH tells you how acidic that solution is, right? What about pKa? What does it tell you? When you just look at, consider this equation here. How what? How basic it is. Can I ask why? Okay. So, well, when you look at the pH, actually, if pH is high, then you can actually say that as this solution is basic, right? So you can actually say that too. pKa is about the acid dissociation constant. So it actually doesn't tell you anything about base, or basic properties. It's only the acid dissociation constant, and you just put the minus log of that. What would that mean? Exactly, the rate of dissociation, how much it will dissociate the proton, basically. Does that make sense? So it's a little bit different. I mean, when you take into account the pH as the acidic measure, it sounds like it's similar, right? But the pH is about the measurement of hydrogen cation itself, as opposed to pKa is about the rate or the ease of the proton donation of that particular substance. So it doesn't have to be specific, acid. It can be base too, but it just is a measure of how much proton is given up.
So you're saying that the pKa is basically how fast like the hydrogens get out of that acid.
So it doesn't directly tell you the rate, how fast that is, but tells you a tendency, how much at the equilibrium, how much it's going to release proton.
So would you say that then like the weak acid release more than strong acid?
So strong acid has a lower pKa value. Lower pKa value means that it has higher Ka value. Higher Ka value means that this is much bigger than this. That means you have a lot of protons released or ionized, right? So in a strong acid, you're going to have much, much more proton released.
And that means lower pKa.
That means low pKa.
Okay.
Yes. So here it is, actually. So there is a relationship between Ka and pKa at the standard state. And as you can see, it's pretty much like highly ranged here. And you can see the pKa value here. The lower, the more acidic, basically. Yes. Rate of dissociated proton and the acid, basically, remaining acid. Yep.
That's essentially the pKa, how much acid dissociate within the solution. And the more acid, the more acidic.
Yes, but it's a really good point because, yes, it is important point because it doesn't have to be in a solution. It's just a property of that molecule itself. I mean, it can be in a solution. Of course, it's easier to measure because water is around and you can just simply, get the amount of hydroxide or protons and things like that. But pKa itself isn't involved in any kinds of reactions. It's just as it is. When you look at the actual equation, sorry, just a whole bit, there's a water involved actually, but we took it out because it's constant, right? So not anymore. But initially, we took it account, we took the account of water molecule, presence of water molecule basically. But it doesn't have to be. It's just a set value there for a certain molecule. So for example, formic acid will always have this pKa value at the standard state. Okay, let's quickly go back to the definition. By the Bronsted-Lowry here, the acid is anything that donates proton, gives up the proton. So whenever something gives up the proton, that's an acid. And strong acid is basically giving a lot of donations, right? It's rich. I mean, it's not really rich, but at least it's willing to give a lot, right, of a proton, not money. All right, so here are some examples, other examples of the Ka and pKa values. Here's a really strong acid, which is a hydrogen chloride or hydrochloric acid, which has the Ka value of 1 × 10⁷ power. And you can simply convert it, right, using this term here. And that's going to be pKa of -7. Make sense? So the pKa value can be -2, and smaller, the stronger acid. Water molecule actually has a pKa value too, as of 14. So you can imagine that anything above 14 can be pretty basic, right? And the interestingly, the hydronium ion also has Ka value of 1, so the pKa will be 0. And that means it's giving out a lot of a proton, right? It's super acidic. Would that make sense to you? Hydronium actually gives up a lot of proton. Does that make sense? How? Anyone back there or? I think you got it. I kind of a little confused with the last part, but I think you got it. Basically, I told you that the water molecule have a poor ionization rate, right? So it'll rather stay as a water molecule, H2O, rather than hydronium, right? So there's going to be only little chance that hydronium actually exists when you just take into account of the whole water molecule in a solution. So hydronium will try to go back to water molecule state. So that's why it try to give up the proton and becomes the water, right? And that is why it has the really low pKa value. To understand further about this pKa and pH, and especially the relationship between those two, we use Henderson-Hasselbalch equation. And we're gonna basically drive that equation together here. I just heard a lot of size here, but I promise you, it's not too complicated once you understand it. So again, this shows the relationship between pKa and pH. And we start from the definition of Ka here, which is the conjugate base, the ratio of the conjugate base and the acid here. So Ka again, sorry about that. The Ka is actually the ratio of the ionized acid, conjugate base, and the hydrogen cation and acid. So here it is, Ka equation. And then we basically drive this equation to make get the H plus concentration. So arrange this equation and move these two guys over to the other side to get the H plus concentration equals Ka. And then this one in the denominator, of course, goes to the denominator now, right? So HA concentration divided by A minus concentration. It's just a simple conversion here. And then we take a negative log 10 here. So let's do that here and put the minus log 10 here too. And now, when you take a look at it here on the right-hand side, you can see that this is log 10 of Ka and something else here. And I just put some rules here, just in case, just to remind you guys. When you look at this, something that is a product of, when the variables and the product of the variables gets into this logarithm, basically it can be divided with the plus, so what you're getting would be the same minus log 10 H plus concentration equals minus log 10 Ka. It should be plus, right? But since there's a minus in front of this logarithm, it's going to be minus log of the remainder here. And this is actually the definition of a pH, right? This is the definition of a pKa. And then you have the rest of it here, minus log HA concentration over A minus concentration. And when you flip this order, I don't know if you can find it somewhere here, but basically you can put out the minus again to make it plus here to get the pH equals pKa plus log the ratio of conjugate base and the acid. And this is Henderson-Hasselbalch equation. So it's actually a pretty simple conversion there. But the really nice thing about this is that now you can relate pH to pKa and vice versa. And especially when you look at this two values inside the logarithm, if the conjugate base concentration is the same as acid concentration, then it'll make this as 1, right? And log 1, you should be able to find it somewhere here. Log 1 should be 0, right? So when these two values are the same, then pH should be the same as pKa. Make sense? And when do you think you can see where the case where the conjugate base concentration is the same as acid concentration? Can you just imagine the case? It doesn't have to be actual like practical case, but think about it. There's always HA becomes H plus and A minus, right? And there should be exact same amount of H plus and HA concentration. That is where, I'm sorry? What is it? Equilibrium. It could be equilibrium, but not necessarily actually. It can happen right in the middle too. What we are talking about mostly is what is really happening at the equilibrium actually. So not the precise answer, but partially answer that. What is it? Conjugate base is what? A conjugate base. So you have a conjugate base and acid, and they're the same concentration, meaning that how much of percentage? I'm talking about the percentage. So let's say that you have 100 molecule of your acid. How much should be basically ionized? All of it? Why? Let's put it that way here. So all of it, meaning that HA is going to be 0, and A is going to be a certain number, right? So it goes to infinity. So it can be quite complicated to calculate this, right? Because pH will be infinity in this case. Exactly, 50%. So if only 50% of your acid is ionized or given up the protons, then you're going to have exact amount of your acid and your conjugate base. Does that make sense? 50-50, so the same amount becomes 1. Okay, so we talked about the acids and its strength now, and its property, we can use that property and make it into a really useful biological system. It's called buffers. And buffers always have a property of titration curves. So we're going to talk about these two things. Buffer system is basically the measures in the living systems used to maintain relatively constant pH. And when you talk about the buffer, it's always pH. It's not about other values. Let's take an example here how buffer system works. So one example would be take a weak acid solution, and we're talking about here acetic acid here, and this is the structure of acetic acid that gives up the proton, basically hydrogen cation, and becomes the conjugate base. And we're gonna just call this anion conjugate base as AC here for simplicity. And what you do is basically gives the strong base little by little to that weak acid. And this strong base has the hydroxide, of course. They're gonna, since it is a strong base, it's gonna release a lot of hydroxide or hydroxide equivalent, something that is pretty negative, negatively charged. And we can think of two equilibria occurring at the same time for this reaction, where there's a weak acid and we're adding the strong base little by little. First reaction and first equilibrium would be here's a weak acid, so they're gonna be hydrogen cation already exist, and you're adding little by little of this hydroxide to make it into water molecule, right? And this reaction will go basically forward because water is poorly ionized. So whenever you see the available hydrogen cation or hydronium and you have hydroxide, it will just instantly get together and becomes a water molecule. But whenever this happens, you should remember that this reaction always follows in this, should satisfy this Kw, ionic product all the time, where it says that the product of this hydrogen cation and the hydroxide concentration should be always 10 to the minus 14th power. And the second equilibrium, second reaction, for the second reaction would be actual acetic acid that is ionized to give up the hydrogen cation. So H plus is released, and it leaves the conjugate base, which is AC minus here. And also, since this acetic acid has its own pKa, it should follow this basically satisfy this Ka value too, which is 1.74 times 10 to the minus 5. And these two conditions should always be satisfied when you're starting keeping the titration, right? You give a little bit of strong base, then there's one reaction initiated, and it goes, and then we'll meet the equilibrium, right? Two equilibria here, basically. And then you add a little bit more, then another reaction goes on, and then we'll meet the second equilibria, things like that. So here again, there are two equilibria here with the different Kw, and these two equilibria basically are governed by one by Kw and one by Ka value here. And when you look at the first equilibrium here, where water molecule is generated, adding we'll keep adding the hydroxide, so we're gonna keep generating the water molecule, right? So we're pushing this reaction equilibrium to the forward direction here. And it still should always satisfy this 10 to the minus 14 relationship here. That means you're actually consuming the H plus there. So H plus is there, right? It's not newly added, as opposed to hydroxide or hydroxide equivalent is added, keep added, right? So you're consuming and using it up hydrogen cation to make the water molecule here. For the second equilibrium, since hydrogen cation is consumed, so it's getting, basically gotten rid of. So you're gonna have more of this acetic acid there. So it'll push the reaction again forward to generate more of this to satisfy this Ka value to become the equilibrium. Make sense? So you're getting rid of H plus, in this equilibrium too. To make it as an equilibrium, you need more H plus there, right? So you're consuming acetic acid basically, and ionize these acetic acid into conjugate base and the hydrogen cation. So this is keep working basically, and the end result of this reaction, which is reaction number 1 plus reaction number 2, would be using the acetic acid and dissociated into the hydrogen cation and the conjugate base. And again, hydrogen cation is also consumed because it has to be, react with the hydroxide to become water. So all this process during the titration curve, during it's a titration, right? Titration process. What you're doing is giving the opposite thing. If it is acid, giving the base. If it is base, giving the acid, and try to make it neutral, consuming the acid or base that you're titrating. And by the process of this titration, you can get the titration curves where you can plot the pH value changes along with the amount of hydroxide equivalent that you're putting in. So when you look at this graph, on the x-axis, it actually says hydrogen cation ion dissociated. And it is a dissociation of the proton, right? So it's the same as association or the addition of the hydroxide or hydroxide equivalent. So this plot basically, again, shows the relationship between this pH, how it is changed on the changes or addition of the hydroxide or the hydroxide equivalents there. You know, and it always interestingly have sigmoidal shape like this, sort of S shape. And when you look at the different acids or even base, they actually have a pretty similar sigmoidal curve there. But only the difference is that it is shifted along the y-axis, the pH scale. And that gives you a really interesting property there where you can use buffer in the range of different pH. And right in the middle, there's an inflection point, you know, so when the curve changes. Right in the middle, that this is a 50% of ionization of that acid. See? So the concentration of acid is the same as the concentration of conjugate base or even proton that is released from this acid. And this is where pH equals pK. And we already talked about that, right? This is the Henderson-Hasselbalch equation. And we're talking about the right midpoint where the concentration of these two are the same. So this is going to be log 1. So just leaves the pH equals pKa, right? Importantly, around the midpoint, even if you add more of the hydroxide equivalent or getting rid of or putting just less of that, you can see that the curve is pretty like flat, right? As opposed to these regions where there really dramatically changes here and here too. And this region where the pH changes is kind of smooth, not much. We call it as a buffer zone, buffer. So depending on what kind of acids that you're using, you're going to have different buffer zones. Make sense? All right, let's keep talking about this property of buffer or buffer zones. So buffer typically have the range of around plus and minus 1 pH unit. So this is highlighted in different colors here for the different acids here. And beyond this plus and minus 1 pH, you're going to have dramatic changes in pH when you titrate this acid with the base. So these are not the optimal region where you can take it as a buffer. But as opposed to when you use this acid within this range of a pH plus and minus 1 around the inflection point, then they're going to behave as a buffer. Should not change much of pH, even if a lot of addition of the hydroxide or not. And there are some examples of the buffer system in our system. So the pH of the blood is around 7.35 to 7.45, and it's buffered by this bicarbonate carbonic acid system where pKa is around 6.1. So think about it. Right at the midpoint, pKa is the same as pH, right? And pKa is about 6.1. So let's take it somewhere here, 6.1. And then your blood pH should be around 7.3 or 4, right? So it actually have the buffer zone covering that range, even up to, like 7.8 or 9 or something like that. So it definitely covers that pH region, range where you can slow down the changes of pH. Another example is a pH for the intracellular fluids, and that is buffered by the phosphate system, where you can see the many different changes here of the same molecule, basically, hydrogen phosphate in the hydrogen diphosphate, dihydrogen phosphate, and things like that. And the pKa value is 6.86. Again, you can just take it the midpoint and just estimate where the range could be, and it's around that physiologically neutral kind of condition too. And another example is a histidine system where pKa is again 6.05. So it's kind of similar range, and that kind of makes sense. Our body system is around kind of 7 point something, like pretty neutral. Then there are these two questions. Do all acid and base have titration curves? What do you guys think? I mean, I talked about using the weak acid and adding the strong base to get the titration curve, right? Which shows this sort of sigmoidal shape. What about other acids and other bases? Do you think all of them have the titration curve? What do you think? What is it? Why not? So everything will have titration curves, although you're not gonna see this kind of similar sigmoidal shape for all the acids and base. It only works for weak acids and weak base. And that's why those weak bases and weak acids are important for biological systems used as a buffer system. We don't have much time, so we should, go a little faster. Can all acid and base be used as buffer? Of course not, right? Because like I told you, only weak acid and weak base should be used as buffer. There are some other acids that releases proton multiple times during titration process, and it's called a polyprotic acid. And polyprotic, as its name says, it releases more than one proton. And each proton that is released have its own characteristic pKa value for that. And pKa is again about the releasing one proton, right? Releasing one hydrogen cation there. Because it's releasing multiple ones, it'll have each of multiple pKa's. One example is phosphoric acid here, which have multiple steps of the titration curves. So the first one is phosphoric acid becomes to dihydrogen phosphates, where it has like a 2-ish of the pKa value. And then it goes to the next phase. Now this dihydrogen phosphate becomes hydrogen phosphate. It has its peculiar pKa value here too. And again, this product becomes just a phosphate ion, have another one. And this is not just inorganic acids, but even amino acids. Hopefully you guys know what amino acids are. We haven't gotten there yet, but at least you know what they are. The amino acids are the building blocks of the protein, right? And they have multiple dissociable proteins too. At least they actually have at least 2 pKa's, one from the one side of one functional group, and the other for the other functional group that are involved in peptide bond, basically. And this amino group and the carboxylate are located at different ends of the amino acids. So one example here is the glycine, which is the smallest amino acid, has a side chain as H. And I just missed saying this, but for the bulkier amino acids, which have more stuff on the side chains, can also release protons there too, right? So it's going to have a multiple, more than 2 pKa's there. So for glycine, both functional groups can be protonized, meaning that I'm gaining protons. So instead of NH2, it's going to be NH3+, and the same for the carboxylate too. And also, it can just lose one of these protons, deprotonated, and also both of them too. So it's going to be both deprotonated or non-protonated. And this mid stage where only one of these functional group is deprotonated is called Dipyridine. And does anyone heard of what Dipyridine is? That is correct. It doesn't have to be amino acid though. It can be any kinds of molecules that is both positively charged and negatively charged on the different sides, basically. So it's going to build up some kind of charge there, right? But the net charge is neutral for the Dipyridine. And for the complex macromolecules like a DNA, RNA, proteins, and things like that, they're going to have a multiple titration curves, basically, because it's not just simply 2 or 3 pKa's, right? each amino acids or each nucleotides have its own pKa's, maybe 2 or 3 or more, right? And it consists of like hundreds of them or thousands of them. So it's really almost impossible to look at the titration curves and look at that inflection points and things like that. We just talked what Zebira Ryan is, but this is quite important. So does anyone answer to this question? Or Zebira Ryan's dipoles? So we talked about the dipoles, right? Can anyone say what definition, what a dipole is? Partially positive charged and partially negative charged. That is correct. Then is Zebira Ryan. Is it a dipole? That's my question, actually. You think it is? Because? Because it's neutral net charge. Dipoles can be neutral too. There's a delta plus, delta minus that builds up the dipole moment, right? And that is actually happening inside of the molecule. So the net charge can be 0 there, or transiently, positively charged or transiently negatively charged, but it definitely can be neutral too. Any other thoughts? Any other opinions on that? Is the Zebira Ryan a dipole? Or we don't care? I may make it into my exam question. Are dipoles? It's okay. Does anyone thought differently? You got it. So it's actually not about partially charged or not. It's all about the dipole moment that it builds up or not. And that happens inside of the molecule, right? As opposed to Zebira Ryan, it's not about the electrons that is shifted inside the molecule. It's just literally charged at a certain group, certain functional groups. So it's not about the movement of electron within the molecule, which dipole is, but it's about some other stuff that comes onto that molecule and make it positively charged or negatively charged based on pH and things like that. So the answer is no. Make sense? So this is the last slide, and we have like 4 minutes or so. We talked about the buffering system and titration curves. Now let's take an example here in the actual physiology. We're going to talk about the blood buffering, which uses the bicarbonate carbonic acid system. So this is carbonic acid that becomes basically releases a proton here, H plus, and becomes a bicarbonate, which is basically conjugate base for this reaction. And carbonic acid level is determined by the concentration of carbon dioxide dissolved in blood because of this another reaction here where CO2 reacts with the water molecule to becomes a carbonic acid. So carbonic acid is not something that is injected into the blood system, but it's just naturally occurred from the dissolution of the carbon dioxide into the blood system where water is everywhere. And this carbonic acid can be also expired in lungs, basically going backward here, right? And releases the carbon dioxide from the blood system. So when you put these reactions together, it's going to be carbon dioxide water molecule becomes carbonic acid, and that also can changes to the releasing the hydrogen cation and the bicarbonate. And when blood is too acidic, and acidic meaning that you have excess of proton or hydrogen cation. So that means this side of the reaction is skewed like much more. So it's higher. Then here, the reaction should go back to left to meet the equilibrium, basically. Does that make sense? It's all about the equilibrium, right? You have much of this stuff, so you want to go back to here to go back to normal. So in order to do so, this to get this one, more of this one, you have to get rid of this one, right? So to get rid of this one, you have to push this reaction here into like to the left, like a reverse direction, right? Does that make sense? If you get rid of this a lot, then you're gonna actually get rid of some of this. And then that'll lead to the removal of this too. That's all about the balance, equilibrium. So you basically push out the carbon dioxide out of the blood in lungs. So this level will decrease. Because this level decreases, now this reaction will be pushed backward, reverse, to get more of carbonic acid and getting rid of this excess hydrogen cation. And in case of obstructive lung diseases, this process cannot occur, meaning that it cannot clear the carbon dioxide from the blood, which can lead to the acidosis, which lowers the pH value, and that can be pretty detrimental. The opposite case would be the blood is too basic. Now you have too low, less amount of this hydrogen cation, in which case the reaction should go to the right direction now to meet the equilibrium, right? So that means you have to have more of this carbonic acid. In order to do so, you have to get a lot more of carbon dioxide into the blood circulation system. So you get more carbon dioxide into the blood in the lung, leads to the increase of carbonic acid. That leads to the increase of the concentration of hydrogen cation. And the disease like the hyperventilation, basically too much of a ventilation, so it releases carbon dioxide too much. You're going to lose carbon dioxide too much, which can lead to the loss of this hydrogen cation, which is alkalosis. Then pH will be increased, so it is also a bad news for your body. All right, so that's it. And have a nice weekend.